Today we talk about observables and permission operators. Observables and permission operators. So we've said that an operator Q is permission. In the language that we've been working so far, if you find that the integral dx psi 1 q psi 2 is actually, with psi 1 star here, equal to the integral dx of q acting this time on psi 1 all star psi 2. So, as you've learned already, this requires some properties about the wave functions far away at infinity, some integration by parts, some things to vanish, but this is the general statement for a large class of functions. This should be true. Now, we want to sometimes use a briefer notation for all of this, and I will sometimes use it, sometimes not, and you do whatever you feel. If you like to use this notation, use it. So here's a definition. If you put a psi 1, comma, psi 2, and a parenthesis, this denotes a number, and in fact denotes the integral of psi 1 star of x, psi 2 of x, dx. So whatever you put in the first input ends up complex conjugated. What you put in the second input, it's like that. It's all integrated. This has a couple of obvious properties. If you put a number times psi 1 times psi 2 like this, the number will appear together with psi 1 and will be complex conjugated. So it can go out as A star, psi 1, psi 2. And if you put the number on the second input, it comes out as is. Because the second input is not complex conjugated in the definition. With this definition, a permission operator, Q is permission, has a nice look to it. It becomes kind of natural and simple. It's the statement that if you have psi 1, comma, q psi 2, you can put the q in the first input, q psi 1, psi 2. This second term in the right-hand side is exactly this integral here. And the first term in the left-hand side is the left-hand side of that condition. So it's just maybe a briefer way to write it. So when you get tired of writing integral dx of the first, the second, that you can use this notation. Now, we've discussed last time the expectation values of operators. So what is the expectation value? Expectation value of q in some state psi of x. And that is denoted as this braces here, and psi is equal to the integral of psi. That the expectation value depends on the state you live in, and it's psi, q, psi, or if you wish, dx in the new notation, psi, q psi. put the hats over. This is the expectation value of Q. I'm sorry, I missed here a star. So far so good. We've reviewed what a permission operator is, what an expectation value. So let's begin with some claims. Claim number 1. The expectation value of Q with Q Hermitian. So everywhere here, Q will be Hermitian. Expectation value of Q is real. A real number. It belongs to the real numbers. So that's an important thing. You want to figure out the expectation value of Q. You have a psi star, you have a psi. Well, it better be real if we're going to think, and that's the goal of this discussion, that permission operators are the things you can measure in quantum mechanics. So this better be real. So let's see what this is. Well, Q psi, that's the expectation value. If I complex conjugate it, I must complex conjugate this whole thing. Now, if you want to complex conjugate an integral, you can complex conjugate the integrand. Here it is. I took this right-hand side here, the integrand, I copied it, and now I complex conjugate it. That's what you mean by complex conjugating an integral. But this is equal integral dx. Now I have a product of two functions here, psi star and Q that has acted on psi. So that's how I think. I never think of conjugating Q. Q is a set of operations that have acted on psi, and I'm just going to conjugate it. And the nice thing is that you never have to think of what is Q star. There's no meaning for it. So what happens here? Product of two functions, the complex conjugate of the first. Now, if you complex conjugate something twice, you get the function back. And here you got Q psi star. But these are functions, you can move them around, so it's Q hat psi star, Q psi. And so far, so good. You know, I've done everything I could have done. They told me to complex conjugate this, so I complex conjugated it, and I'm still not there. But I haven't used that this operator is Hermitian. So because the operator is Hermitian, now you can move the Q from this first input to the second one. So it's equal to integral dx psi star Q psi. And oh, that was the expectation value of Q on psi. So the star of this number is equal to the number itself, and that proves the claim Q is real. So this is our first claim. The second claim that is equally important, claim 2. The eigenvalues of the operator Q are real. Of Q are real. So what are the eigenvalues of Q? Well, you've learned with the momentum operator, eigenvalues or eigenfunctions of an operator are those special functions that the operator acts on them and gives you a number called the eigenvalue times that function. So Q, say, times psi1, if psi1 is a particularly nice choice, then it will be equal to some number, let me call it Q1, times psi1, and there I will say that Q1 is the eigenvalue. That's the definition, and psi1 is the eigenvector, or the eigenfunction. And the claim is that that number is going to be real. So why would that be the case? Well, we can prove it in many ways, but we can prove it kind of easily with claim number 1 and actually gain a little insight. Calculate the expectation value of Q on that precise state, psi1. Let's see how much is it. You see, psi1 is a particular state. We've called it an eigenstate of the operator. Now you can ask, suppose you live in psi1. That's who you are. That's your state. What is the expectation value of this operator? So we'll learn more about this question later, but we can just do it. It's the integral dx psi1 q psi1. And I keep forgetting the stars, but I remember them after a little while. So at this moment, we can use the eigenvalue condition, this condition here, that this is equal to dx psi1 star q1 psi1. And the q1 can go out, and it's q1 integral dx of psi1 star psi1. But now, we've proven in claim number 1 that the expectation value of Q is always real, whatever state you take. So it must be real if you take it on the state psi1. And if the expectation value of psi1 is real, then this quantity, which is equal to that expectation value, must be real. This quantity is the product of two factors. A real factor here, that integral is not only real, it's even positive, times q1. So if this is real, then because this part is real, the other number must be real. Therefore, q1 is real. Now, it's an interesting observation that if your eigenstate, eigenfunction, is a normalized eigenfunction, look at the eigenfunction equation. It doesn't depend on what precise psi1 you have, because if you put psi1 or you put twice psi1, this equation still holds. So if it holds for psi1, if psi1 is called an eigenfunction, 3 psi1, 5 psi1, minus psi1 are all eigenfunctions. Properly speaking, in mathematics, one says that the eigenfunction is the subspace generated by this thing by multiplication, because everything is accepted. But when we talk about a particle maybe being in the state psi1, we would want to normalize it, to make psi1 integral squared equal to 1. In that case, you would obtain that the expectation value of the operator on that state is precisely the eigenvalue. When you keep measuring this operator on the state, you keep getting the eigenvalue. So I'll make that a comment for a normalized psi 1 as a true state that you use for expectation values. In fact, whenever we compute expectation values, here is probably a very important thing. Whenever you compute an expectation value, you better normalize the state. Because otherwise, think of it, the expectation value, if you don't normalize the state, you do the calculation and you get some answer, but your friend uses a wave function is 3 times yours, and your friend gets now 9 times your answer. So for this to be a well-defined calculation, the state must be normalized. So here we should really say that the state is normalized. Psi 1 is the eigenfunction, normalized. And this integral would be equal to Q1 belonging to the reals. And Q1 is real. So for a normalized psi 1, or how it should be, the expectation value of Q on that eigenstate is precisely equal to the eigenvalue.